Welcome to the composition of solutions, by which we really mean we're talking here about concentration. So, often we perform chemical reactions in solution because it's easy to mix chemicals in aqueous solution, and to perform stoichiometric calculations in such a case where we have a solution, then we need to know the state the reactants exist in while in solution. We need to know the balanced chemical equation, and we need to know the concentration of the reactants in solution. So what do we mean here by the state the reactants exist in while in solution? Well, what we mean is when we dissolve our substance into whatever our solvent is, in most cases it's going to be water. Whenever we dissolve our solute in water, we have something that could happen. We could either dissolve the whole molecule in water, as we have in the case of, say, sugar. We take sucrose and we put it into water. The whole sucrose molecule dissolves in solution, and it stays together as a molecule as it floats through solution. But if we put something like salt, table salt, sodium chloride in solution, the sodium and chloride ions separate from one another. They get hydrated, and so the cations and anions are able to move around separately from one another. We don't have a sodium chloride molecule where we have a sodium ion and a chloride ion stuck together, moving around together. They're able to move around independently. So that's what we mean by the state the reactants exist in. In the case of the sugar, it's a molecular form. In the case of the salt, we have ions floating around in solution. And that means that they are able to act independently of one another. What the sodium ion does and what the chloride ion does don't affect each other. So, now let's talk a little bit about concentration. We have a few different ways of measuring concentration. The first that we're going to talk about is molarity, symbolized with a capital M. This is a unit of concentration that's defined as the moles of solute per volume of solution in liters. So, molarity is equal to moles of solute divided by liters of solution. Now note here that this is liters of solution, not liters of solvent. So, if we take some number of moles of our solute, let's say sodium chloride, and we dissolve it in 1 liter of water, the solution is likely to have a larger volume than 1 liter, right? Because now we've added some sodium chloride to that 1 liter's worth of water. So what we need to know is we need to know the volume of the solution after we've dissolved our solute in the solvent. So a solution that is 2.5 molar, so we can abbreviate molar as capital M, 2.5 molar, contains 2.5 moles of solute per liter of solution. So note that our denominator is liters of solution, again, not liters of solvent. So let's look at an example here. Concentrated hydrochloric acid, which has a molar mass of 36.46 grams per mole, contains 856 grams in 1.94 liters of solution. So what is the concentration of hydrochloric acid in this case? Well, again, we know that molarity is equal to moles of solute divided by liters of solution. We know that we have 856 grams of hydrogen chloride, but that's not moles. So we need to convert from grams to moles. We know the molar mass is 36.46, so we divide by their molar mass, convert into moles, and divide by our volume of solution, 1.94 liters, and that gives us a concentration of 12.1 molar. So we can also calculate the concentration of ions in solution. So if we want to know what the sodium ion concentration is in 1 molar sodium phosphate, note here that this X, something in brackets, so in this case the sodium ion, means the concentration of X. So in this case the concentration of sodium ion, or the X concentration, the sodium ion concentration. So we know that we have 1 molar sodium phosphate, but we know that in 1 mole of sodium phosphate we have 3 sodium ions. So we have 3 moles of sodium ions in that 1 mole of sodium phosphate. And that means that because we started out with 1 molar sodium phosphate, we end up with 3 molar of sodium ions. So often we need to know what volume of a solution we need to obtain some amount of a solute. So, for example, blood serum contains 0.14 molar sodium chloride. So what volume of blood contains 1.0 milligrams of sodium chloride? Well, we know our concentration, 0.14 molar sodium chloride. We know that that equals 0.14 moles of sodium chloride per liter of solution. And we know that 1.0 milligrams of sodium chloride is what we want. So let's convert that into grams. So we get rid of milligrams, put in grams. And now we know the molar mass of sodium chloride, 58.44 grams of sodium chloride per mole. And we know that our concentration in blood was 0.14 moles of sodium chloride per liter of solution, per liter of blood. And that means that in order to get our 1 milligram, we need 0.12 milliliters of solution. So we need less than a milliliter of blood to get our 1.0 milligrams of sodium chloride. So we often want to make a less concentrated solution by adding more solvent to a more concentrated solution. And this process is called dilution. So we often dilute a stock solution to get a larger volume of a lower concentration solution. So during dilution, the number of moles of solute is not changing. So we're just taking our solute and we're just spacing out the solute particles some, because we're just adding in more solvent. So again, the number of moles of solute is not changing, while the volume of solution is changing. So this means that the moles of solute before dilution have to be equal to the moles of solute after dilution. So suppose we want to prepare 500 milliliters of 1.00 molar acetic acid from 17.4 molar acetic acid solution, stock solution. So first we need to know how many moles of acetic acid we need. Well, we want 500 milliliters of solution. Let's convert that into liters so we can use molarity. And then we want a solution that is 1 molar. We know that that's 1.00 moles of acetic acid per liter of solution. So note here that now our liters of solution will have gone away, our milliliters of solution will have gone away, and now we'll end up with units of moles. So we need 0.500 moles of acetic acid. So now we know how many moles of acetic acid we need. So now we need to find the volume of our stock solution that we need in order to obtain our half a mole of acetic acid. So we start out with our half mole of acetic acid. We know that the concentration in our stock solution is 17.4 molar. So I'm dividing by 17.4 molar here. So 17.4 moles of acetic acid in 1 liter of solution. And that gives us 0.0287 liters of solution. And then we can convert from there, I haven't done the math here, but into milliliters, or I haven't shown the math here. So 28.7 milliliters of solution of our stock solution is what we need. So we're converting from 28.7 milliliters into 500 milliliters, and that will give us our 1 molar solution that we want. So while the above example is the dimensional analysis method of calculating the volume needed, there's a shortcut. So I prefer the dimensional analysis method because for me it's a little bit easier to see what exactly it is that I'm doing and to make sure that I'm not making any mistakes. But we can use this shortcut M1V1 equals M2V2, where M1 is the concentration of the stock solution, V1 is the volume of our stock solution, M2 is the concentration of our diluted solution, and V2 is the volume of our diluted solution. So note that you still need to ensure that your units are canceling correctly here. And that is, you can't list one volume in liters and the other volume in milliliters, or concentrations in millimoles, and the other in molar. So in the last example, we knew that we had a concentration of our stock solution, so we knew M1. We knew that we wanted a concentration and we wanted a certain volume of our diluted solution, so we knew M2 and V2. So all we had to do was rearrange and solve for V1. So we can do that here. So again, we want to prepare 500 milliliters of 1 molar acetic acid from our 17.4 molar acetic acid stock solution. So we know M1, we know M2, and we know V2. So we rearrange to get V1. V1 is equal to M2 V2 over M1. And that means that When we plug in our values, we have 1.0 molar acetic acid times 500 milliliters divided by 17.4 molar acetic acid, and that gives us the same 28.7 milliliters that we got with the dimensional analysis method. So, in my classes, you're welcome to use the shortcut method, but you need to be careful that you're performing the algebra correctly, the algebraic rearrangement correctly, and that you're plugging in the correct values for the correct variables. Right? You need to make sure that you're not swapping, say, M1 and M2 or V1 and V2. But I don't care which method you use, whether you use the dimensional analysis method that I showed first or the shortcut method, the M1 V1 equals M2 V2. Either way is fine. Just make sure that whichever way you're doing it, you know that you're doing it correctly. So that was the composition of solutions, where we talked about concentration.